Hey everybody, so I am going to make videos specifically for exactly what the AP is going to cover with regards to sequences and series. I'm going to try to make them no longer than like 10, maybe 15 minutes a piece, but that might mean I need to break things up into like an intro with an example and then one example at a time. I just wanted to make them so that they weren't too overwhelming and you could come to them when you want to, rather than having to scrub through and figure out where you left off. So hopefully that works for you. We're going to try it, see how it goes. Um, I do have longer videos for much of this, not all of it, on my website, but those videos were made with the intent of I teach you through a video and then we talk, face to face. But there is no talking face to face right now because this is as close to my face as you're going to get. Um, and yeah, I can't see you and ask questions live. So just bear with me. Please, please, please email me or send me a remind. You can record a video and send it through remind, whatever you want. But try to ask me questions if you have any. I'm happy to answer them. So before I ramble on and get too far, I'm going to try and keep my face in the corner because I feel like if you can see my face, there's a little bit more of a personal connection. I'm not doing my hair or putting on makeup for you guys. Sorry. So you get whatever I'm wearing at the time and whatever cat butt decides to get in my way while I work. Um, I need you then to get out your packet that your BC sequence and series notes are in and go to page 10, and it should look something like this. It should say Maclaurin Series, um, and it should be on page 10. I believe my page numbers are the same as yours, and I'm just going to start here. Please know I am not going to go through and teach you all the nitty-gritty details. I would love to because they're interesting details, but for right now, we just don't have that kind of time. All right, so I'm going to flip this. So you're going to see the sky here. And speaking of cat butts, here comes a Pete. Um, so what we have here is, hi Pete. Yep, that's Pete. Okay. What we have here is a Maclaurin series. So what I'm about to do is instead of using geometric series to create a series that represents a function, I'm going to use a different kind of pattern to create a polynomial that can represent any kind of function. Before when we did it, it was only starting with or branching out from a over 1 minus r. Now we're going to do it for anything. Doesn't have to be in that a over 1 minus r form. So the general format for these series are I call it a Taylor series. Taylor series is when you take any kind of function and create a polynomial for it. And if you center your Taylor series at x equals 0, that's called the Maclaurin series. So Taylor series can be centered anywhere. Maclaurin are the specific types of Taylor series that are centered at 0. So you're going to see both. The most important term underneath that is this thing right here, which is the same thing as that. To create a Taylor series, each term is created by taking the nth derivative. That's what where is it? I need my pen. The nth derivative, and then evaluating it at 0, dividing by n factorial, and then multiplying by x to the n. So let me just go through an example. I think once you see an example, you realize, oh, this really isn't that bad. It's just confusing to look at first. All right, so let me get a good looking pen here. Let's do that one. So if I want to make the 7th degree Maclaurin polynomial, since it's the 7th degree, I need to go through 7 derivatives. And since it's a Maclaurin polynomial, I need to evaluate all of those derivatives at x equals 0. And since I'm using f of x equals sine x, that's the function that I'm mimicking with a polynomial. So f of x equals sine x. And now I need to take 7 derivatives. So the first derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. The fourth derivative is positive sine. The fifth derivative, back to cosine. The sixth derivative, negative sine. The seventh derivative, is what? Negative cosine again. Then what we need to do is evaluate each of those at x equals 0. So if I find f of 0, I'm going to get 0. F prime of 0 is cosine 0, that's 1. F double prime of 0 is 0. F triple prime of 0, negative 1, and so on. Okay, so all I did is I plugged 0 in for each of these x's and then evaluated it. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is still 0. All of these things that I just wrote out, these become my numerators. The denominator, so we just did this up here, the denominator is always over n factorial, where n is the number of the derivative you took, and then you multiply by x to the n. So what we've just done is we have realized that sine x can be approximated by doing 0 over 0 factorial x to the 0, because that was the 0th derivative, which is your original function. Then I take the first derivative, 1 over 1 factorial x to the 1. And then I'm at the second derivative, 0 over 2 factorial x squared, negative 1 over 3 factorial x cubed. And now I'm at the fourth, 0 over 4 factorial x4, 1 over 5 factorial x5. Nope, not equals. Sixth derivative, 6 factorial x6. Seventh derivative, 7 factorial x7. Now, when we are asked to do these things, if I want the 7th degree Maclaurin, that means go out to x to the 7th, which I did. And then typically we don't write the terms that have zeros in them. So I'm going to go through and simplify this down a little bit. And that means the sine of x can be approximated by, okay, now maybe you're thinking, wait, Mrs. Weber, hold on. What is happening there? 0 factorial. Well, I'm going to actually define 0 factorial using 7 factorial. I know that seems weird. Remember, or possibly learn for the first time, factorials means multiply down. So 7 factorial means 7, 6, 5, 4, 3, 2, 1. Which means 7 factorial is 7 times 6 factorial, right? Using that recursive definition of factorials, that would mean 1 factorial is the same as 1 times 0 factorial. And so by definition, because we don't want math to get broken, it is defined that 0 factorial equals 1. It's just one of those things. It's like 4 to the 0 power equals 1. Part of it is because we said so. If you want to know more about it, you can take real analysis and find out more about it. But for now, just trust me that because I said so, 0 factorial is 1. So this term is 0 divided by 1 times 1, which is 0. So that's gone. Therefore, this is gone, and that's gone. So anything with a 0 in the numerator has since disappeared. And then everything else becomes 1x to the first, negative 1 over 3 factorial x cubed, plus 1 over 5 factorial x5, minus 1 over 7 factorial x7. And if you notice, there's a pattern here where you're only using the odd terms. All of them have factorials on the bottom. All of them have ones on top, and they alternate sign going plus, minus, plus, minus, plus, minus. And if you don't believe me, if I quickly come back to my favorite, I'm going flip this open again. Sorry if I'm making you dizzy. If I go to Desmos, if I type in sine x, there's sine x. And if I type in the series for sine x, we have x minus 1 over 3 factorial x cubed. Yes, it can handle factorials. Plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh. Oh, that didn't go the right way. Look at how good that looks. I mean, it's gorgeous. And believe it or not, the more I go, I can make this fit everywhere. So if I went out, pardon me, to like, I don't know, let's just do two more. Let's do x to the 11th. 1/9, x to the 9th, hi Pete, minus 1/11, x to the 11th. I now have, if you look at that, one full cycle, one full period of the sine curve. I mean, look at how close that is. If I zoom in here, there's one period of the sine curve. I can't even tell the difference between negative pi and pi. And I've only used what, 5 terms? No, 6 terms. I think I went out to the 11th. I've only used 6 terms. So that's the power of doing these. That's one of the reasons that they kept it on the AP exam, is that this is just a really powerful thing. All right, so to create a Taylor polynomial, you take the nth derivative, put it over n factorial, and then multiply by x to the n. So I'm going to stop this video here, and then I'm going to come back and do different examples at a time. If you think you understand how this worked, the next example here works a lot like this one. So what I'll probably do in the next video, you know what, I am going to do it. In the next video, I will start it with this question done already, and then you guys can check your answer against mine. All right. So the next video will start with this one right here done, and then I will go on and talk about this next type of Taylor series. Okay. Again, you'll see a YouTube link up there, but I think I go into more detail than you really need right now. Okay, so I am done. I've got to end these with a joke, and so the jokes are coming from my kids now. Max's joke was, what day has the fewest clouds? And that would be Sunday. So Sunday, fewest clouds. It works for a 6-year-old. I thought it was pretty good. All right, toodles.